In this chapter, we will talk about the topic 3, which is a top-level view of computer function and interconnections. First of all, we'll go into the computer components. The contemporary computer design are based on concepts developed by John von Neumann and is referred to as von Neumann architecture, and it's based on 3 concepts. It's a data and instructions stored in a single read-write memory. The content of this memory are addressable by location without regard to the type of data contained here. And execution occurs in a sequential fashion from one instruction to the next. There are 2 approaches in computer, which is the programming in hardware and programming in software. First, we'll look into the software. Software is a sequence of code or instruction, and it is part of a hardware interpret each instruction and generate control signals. Software also provided a new sequence of code for each new program instead of rewriting the hardware. And there are the major components of the computer is the CPU, which acts as the instructions interpreter, and the modules of general purpose arithmetic and logic functions, and I/O components, which acts as the input and output module. For the memory, we have a memory address register, which is the specifies the address in memory for the next read or write, and memory buffer register, which contains the data to be written into memory or receive the data read from memory. For the register, we have I/O address register, which specifies a particular I/O device, and the I/O buffer register, which is used to exchange the data between an I/O module and the CPU. And this is the diagram of the top level view of our CPU, which consists of PC, MLR, IR, MBR, I/O address register, and I/O buffer register, and all those I/O modules. For basic instruction cycle, they start from here, and then fetch that instruction, and then they execute the instruction, and then they halt. And for any excessive information, they will just redo the cycle until all the instructions are done, and then they will halt the program. We look at the fetch cycle. At the beginning of each instruction cycle, the processor fetches an instruction from memory. The PC holds the address of an instruction with fetch next, and the processor increments the PC after each instruction fetch so that it will fetch the next instruction in sequence. The fetch instruction is loaded into the instruction register, and then the processor interprets the instruction and performs the required action. This is the example of our program execution, which normally consists of 6 steps. And first of all, the memory will store into the instruction register, and then memory will store the register into the accumulator, and then the memory will the PC will be they will increment the PC, and then the next memory in the address will update the instruction register, and therefore in the next step they're updating the accumulator and increment of the PC, and so the next step, the next address will update the IR with their memory, and at last the accumulator will update back to the memory. Next, we'll look at the classes of interrupts. There are 4 interrupts, which consist of a program interrupt, which they generate by some condition that occurs as a result of an instruction execution. And the timer interrupt, which is generated by a timer within the processor, and this allows the operating system to perform certain functions on a regular basis. And the I/O interrupt is generated by an I/O controller to signal the normal completion of an operation, request service from the processor, or to signal a variety of error conditions. And lastly, the hardware failure, which is generated by a failure such as power failure or memory parity failure, which leads to an interrupt. The diagram above shows the effects of interrupts and how it is effect into the I/O. As you can see, for first diagram there is no interrupt, so the I/O will be very fast. And for the second command, the interrupts and there is a short I/O wait. And the third picture, there's also interrupt, but there's a long I/O wait, which depends on the types of the interrupts. The following diagram shows how the short I/O waits works. The first is the operation without the interrupt, so the black space is where processors wait for, and this one if they interrupt it with the concurrent, and then therefore the I/O will be very fast. Yes. And the next is how they executed the long I/O wait with interrupting. This kind of I/O operations, first of all they operate I/O and then the processors wait. With the interrupt, they operates with the processor, they fill in the blanks and then the processor waits. Therefore that I/O wait is longer. Next we look at the I/O functions. I/O modules can exchange data directly with the processor. Processor can read data from or write data to an I/O module. In some cases, it is desirable to allow I/O exchange to occur directly with memory. Next, we'll look at the computer modules. The interconnection structure must support the following type of transfer, which is the memory to processor, or processor to memory, I/O to processor, processor to I/O, I/O to or from memory, which is the 5 main interconnection structure. Next, we'll talk about the bus interconnections, which is a communication pathway connecting two or more devices. The signals are transmitted by any one device are available for reception by all other device attached to the bus. And it typically consists of multiple communication lines. The computer system contains a number of different buses that provides pathway between components at various levels of the computer system hierarchy. And they are known as the system bus. Next, we look at the data bus, which is the data lines that provide a path for moving data among system modules. It may consist of 32, 64, 128 or more separate lines. The number of lines is referred to the width of the data bus, which means the more of the number of lines, the wider the data bus. And the number of lines determines how many bits can be transferred at a time. The width of the bus is a key factor in determining overall system performance. And there are two more, which is the address bus and the control bus. The address bus is used to designate the source of or destination of the data on the data bus, while the control bus is used to control the access and the use of the data and address lines. The width on the address bus determines the maximum possible capacity of the system and also uses to address I/O ports. Next, we'll look at the QPI, which is the Quick Path Interconnection. It is a multiple direct connections, which direct pairwise connections to other components, eliminating the need for aberration found in shared transmitter system. And it had a layered protocol architecture and packetized data transfers. This diagram shows the layers of the QPI, which is consisted of physical, link, routing, and protocols. And the next diagram is the physical interface of the QPI. Well, next let's look at the link layer of a QPI. The link layer of QPI performs two key functions, which is the flow control and error control. The flow control is to ensure that a sending QPI entity does not overwhelm a receiving QPI entity by sending data faster than the receiver can process the data and clear buffers for more incoming data. While the error control function is that detects and recovers from bit errors and also isolates higher layers from experiencing bit errors. Next, we'll look at the routing and protocol layers of a QPI. For routing layers, that is used to determine the course that a packet will traverse across the available system interconnects, and it is defined by firmware and describe the possible path that a packet can follow. For protocol layer, the packet is defined as the unit of transfer. One key function performed at this level is the cache coherency protocol, which deals with making sure that memory values held in multiple caches are consistent. And lastly, we look at the peripheral component interconnection PCI. It is a popular high bandwidth processor independent bus that can function as a mezzanine or peripheral bus. It delivers better system performance for high-speed I/O subsystems. And this diagram shows the protocol layers of the PCI, which contains of physical layer, data link layer, and the transaction layers. And last but not least, we also look at the PCI Express, which is the point-to-point interconnect scheme intended to replace the bus-based schemes such as PCI. The key requirement is high capacity to support the needs of higher data rate I/O devices such as gigabyte internet. The requirement that deals with the needs to support time-dependent data streams is. And that's all for my description. Thank you.